So in the previous section, we were talking about the simplest types of sugars, which are the monosaccharides. In this section and the subsequent one, we're going to be taking a look at bigger and bigger sugar molecules. So then the next level up of sugar, known as our disaccharides, and the prefix here kind of tells you how big they are or what they're made up of, right? So a disaccharide is a sugar composed of two monosaccharides joined together. And just like with our monosaccharides, we saw that there were three really important monosaccharides. We're going to see three really important disaccharides as well. And they're listed here in this table. All right, so if we stick two glucoses together, we end up with maltose. That's our first disaccharide. If we stick a glucose and galactose together, we end up with lactose. And if we stick a glucose and a fructose together, we end up with sucrose. All right, so these are the three most common disaccharides and the components of what they are actually made up of. All right, we'll take a look at each of these three disaccharides in turn. So maltose was the first one, and this is also known as malt sugar, right? So it's found in your malt products or malt-based products, and it is made up of two glucose units. So two glucoses joined together. Maltose can be made or obtained from the hydrolysis of starch. Hydrolysis just means to break down. Of starch, and it's used in a variety of places. It's used in cereals, to make cereals, candies, brewing, etc. And this can be found in both the alpha and the beta form, right? We talked about alpha versus beta in a couple sections ago. So let's take a look at how maltose forms in the first place. So we said it's made up of two glucose molecules. So on the left side here, we have one alpha D glucose, and on the right side we have another alpha D glucose. So let's revisit that really quick. So we said that it is alpha because the OH on carbon 1 is pointing down, right? That's what makes it alpha. And then what makes it D, right, was the fact that the OH, the hydroxyl group, was pointing to the right in the open chain form. So we have two of these alpha D glucose units. What can happen is they can combine in sort of a head to tail arrangement. So if you were to number these carbons, right, here's carbon 1, 2, 3, 4, 5, and 6. And if I were to number the carbons in the neighboring glucose molecule, 1, 2, 3, 4, 5, and 6, right, what can happen is the OHs from carbons 1, from the glucose on the left, and the OH from carbon 4, the glucose on the right side, right, they can combine together and they can react together to form a new bond between those two glucose units, and that new bond is this bond here that ends up being made. All right, and that's a new bond or a link. And there's a special name that we give to that bond or link. We call it a glycosidic bond or link. Right, so it's a glycosidic bond or a glycosidic link. Those are the bonds that attach sugars, individual monosaccharides together in in bigger and bigger molecules. We can specify now in that glycosidic bond which carbons are being attached to each other. And what carbons are being attached would be the carbon number 1 here from the glucose on the left to carbon number 4 of the glucose on the right side. Right? So we call it a 1,4 glycosidic bond, and specifically it's the alpha 1,4 glycosidic bond because we have the alpha isomer of the monosaccharide that we actually started with, right? So it's a glycosidic bond. It connects carbons 1 to carbon 4, and we use the alpha isomer, so it's an alpha 1,4 glycosidic bond that connects both glucoses together in maltose. All right, so you'll notice here in order to make that bond that we actually remove an OH from one and an H from the other, so we actually lose a water molecule. So it also produces an H2O molecule as one of the products. And we're going to see other types of glycosidic bonds here in a second. They all are going to produce or lose H2O as well. Lactose is the second disaccharide. Lactose is also called milk sugar. That's the sugar you find in regular milk. It makes up a decent percentage of both human and cow's milk. And if you take a look at the bond, the glycosidic bond in lactose, here it is, we can describe it in a similar way to the bond that we found in maltose. All right, so here, to zoom in a little bit. All right, on the left side now we have the beta form of galactose, right? And it's beta because the OH on carbon 1 is pointing up. All right, that's what makes it beta. So we have galactose, and then that's going to combine with an alpha glucose here on the right side. So again, we're going to be combining or linking together the carbon 1 from one glucose to carbon 4 to the other. All right, so that's the part of the thing that's going to change. So the bond that we make then, again, is going to be called a glycosidic bond. We are still connecting carbons 1 to carbon 4. So it's a 1,4 glycosidic bond, but then it's different than the maltose because we're actually starting with the beta isomer of galactose. So when we describe that bond, we call it the beta 1,4 glycosidic bond, right? And our 1,4 glycosidic bond, or beta 1,4 glycosidic bond, is that we produce right here. And as I mentioned before, right, in order to make that bond, we have to lose a water molecule. There's our water that we end up losing. All right, so a glycosidic bond, we're connecting two sugar units together. Specifically, we are connecting carbons 1 to carbon 4, and we use the beta isomer of galactose, so we call it the beta 1,4 glycosidic bond. All right, so lactose is a disaccharide molecule. The third one is sucrose, and sucrose is just a common name for table sugar, right? This is what you use in your kitchen or elsewhere to add to tea or coffee to sweeten it typically. Sucrose is commonly extracted from sugarcane or sugar beets. And sucrose is going to look moderately different than the other two disaccharides. It is made up of glucose, just like the other two were, but the difference now is that second monosaccharide that we combine with glucose, and in this case, we combine it with beta-D fructose. All right, so if we take a look at sucrose down here, all right, we can describe the bond between the glucose and the fructose. So again, here we have our alpha D glucose, so it's alpha because the OH on carbon 1 is pointing down. And we're now going to combine that with beta D fructose. So it's beta because the OH here on our carbon question is pointing up. We're going to combine. We're going to link now together carbons 1 from glucose to carbon 2 from fructose. So we end up now making, again, a glycosidic bond, right, which is just a bond between two sugar units. Now we're combining, or we're linking together carbons 1 to carbon 2. So it's a 1,2 glycosidic bond. And we're linking now the alpha form of glucose to the beta form of fructose. So we call it an alpha beta 1,2 glycosidic bond. You'll sometimes see it being represented this way that I wrote, or sometimes you'll see it being represented that way. In either way, it's a 1,2 glycosidic bond that connects the alpha form of glucose to the beta form of fructose. So that new bond then that we make is this bond here that connects those two things, glucose and fructose, together. All right, so a couple things to note here with sucrose that is very different than both lactose and maltose, and that is that your sucrose cannot form an open chain, and thus it cannot be oxidized, which means it is not a reducing sugar. All right, and the reason why that is because this carbon here that would normally be free and be free to open up in a normal disaccharide, that's actually locked into this glycosidic bond, right? So it cannot open up to be oxidized. Whereas in both lactose, right, you had this carbon here that was free to open up. This can open back up. To form an aldehyde, right, which means that then this can act, lactose can act as a reducing sugar. And similarly in maltose, right, if you'll notice here as well, right, we had this portion of the molecule, the carbon 1 of the glucose that could also open up to an aldehyde, which can then be oxidized, which means that oops, this is still lactose, my apologies. Let's go up here to maltose. So in maltose we still have that carbon number 1 and the neighboring glucose molecule that can open up to expose that aldehyde, which means this can act as a reducing sugar. All right, so in the case of both maltose and lactose, right, these can both be reducing sugars because we have that available aldehyde that can open up and be oxidized. In the case of sucrose though, right, it cannot open up to form that chain because this carbon here is locked. Both of these carbons are locked in that glycosidic bond. So it cannot be oxidized. So this will be then a non-reducing sugar. right? And those are some important differences between each of those disaccharides. So, when we introduced this chapter, we were talking about sugars, and generally, when you hear the term sugar, you may think, well, something that's very sweet, but that may not necessarily be the case depending on the type of sugar that you're dealing with, right? Sugar is just a class of biomolecules or a category of biomolecules. If we were to compare the sweetness of different types of sugars, you may be surprised. All right, so if we take a look here at sucrose for comparison, which is just regular old table sugar, which we assign a sweetness value of 100, right, you'll actually see that several of the sugars are way less sweet. So for instance, the monosaccharides, galactose, and glucose are not very sweet at all, whereas fructose is quite sweet. Right, almost twice as sweet as regular table sugar. The other two disaccharides, like lactose and maltose, right, not sweet at all, whereas sucrose is fairly sweet. And then the sugar alcohols that we mentioned before, right, they are fairly sweet, but definitely not even sweeter than sucrose. There are sugar substitutes or non-carbohydrate sweeteners that you may be familiar with, right? So for example, and you may use these things like stevia, or aspartame, or saccharin, or sucralose, and all these other things, right? They're extremely sweet, right? And you find them in things like Splenda, your artificial sweeteners. They are a lot sweeter than regular table sugar, and that has to do with how they interact with the taste receptors on your tongue, for instance. So here's an example of one of those artificial sweeteners, which is sucralose. Right, so sucralose kind of sounds like sucrose, and when you look at the structure of it, it looks very similar to sucrose. The only difference is some of the hydroxyl groups on sucrose get replaced with chlorine atoms. Right, so for instance, there are a couple chlorines that are replaced in sucrose to make sucralose, and that's what you actually have in Splenda. Aspartame is another one, and you find that in your commercial NutraSweet or Equal. This is a non-carbohydrate sweetener, meaning it's not based on any sugar. It's actually looks more like a different type of a molecule known as an amino acid, which we'll see down the road. But it is also used as a sweetener as well. Okay, so here is another example of a disaccharide. This is called Melibiose, and it's about 30 times sweeter than sucrose, regular table sugar. So let's take a close look at it and see if we can make some sense of the bond or the glycosidic bond that links these two sugar units together. All right, so when you look at it, right, you want to sort of focus in on where these two sugar units are connected, which will be right here. Right, so there's your glycosidic bond. And when you look closely at a glycosidic bond, really what it resembles is an ether, right? You have an O between two carbons, right? So in this case, a glycosidic bond is nothing more than an ether. The only difference is that it's found in a sugar. So what type or which carbons are we connecting in Melibiose? Well, we're connecting carbons 1 to carbon 6 of the neighboring one. So we'd call it a 1,6 glycosidic bond. All right, and then is it an alpha or is it a beta 1,6 glycosidic bond? Well, if you look at where this OH was on our sugar here on the left side, that OH was pointing down originally. So that would make it the alpha form of that bond itself. So this would be an alpha 1,6 glycosidic bond in Melibiose.